Hey, this is Greg from CacheQ again. I wanted to get back to you with another video showcasing our technology. I uploaded a video a little while ago showing targeting our technology on a Zinc MP-SoC device, which is from Xiilinx. It has an ARM, a 4-core ARM device on it running at 1.2 gigahertz connected to an FPGA fabric. And I showed you some performance numbers running an algorithm, a financial technology algorithm called Black-Scholes, targeting just the CPU single-threaded using GCC, along with our multi-threading technology, which automatically partitions the code across multiple cores. And I showed you sweeping that across 4 cores and showing the speed up there. And I also showed you what would happen, what performance you would get by targeting that same algorithm to the FPGA fabric and letting it accelerate there. And this is the graph that I'm showing here. We got some comments about that, about both the ARM being a relatively low performance processor running at a relatively low clock speed for modern CPUs, which is true. It's a typically embedded type of device that we targeted there, but I did it to show you an example of how easy it is to use our technology and to actually target heterogeneous compute platforms with our technology. But the question was, what if you targeted a more appropriate modern x86 CPU and/or the biggest, baddest FPGA that's available today. So I've done that, and I'm going to just demo that for you. I'm going to let it run, and while it's running, I'm going to bring up the specs on this card that I've targeted in my system. This is an Alveo U250 data center accelerator card from Xiilinx. It's a PCI Express card. It has 1.3 million lookup tables available in it, spread across 4 die in a multi-chip packaging substrate that Xiilinx calls SSI, or Stacked Silicon Interconnect. It's one of the largest FPGAs ever built. It's been out just a few years, targeted for data center, and it's sitting in a system that is coupled with an AMD Ryzen Threadripper device with 16 cores on it, and I've run it sweeping, using the exact same experiment as before on the ARM MP-SoC device, but with this system, which has this high performance x86, which is running at 3.6 or 3.4 gigahertz, and this very high performance FPGA card attached to it. So I've run the experiment the same way. I ran single thread GCC on Black-Scholes on the same number of stocks, and then I've swept the multi-threading parameters from 1 to 18 cores, or 18 threads, and then I also targeted the FPGA. And I'm going to load the same sort of graph that I did before here, and I'm going to just plot it with my Python script and show you what the equivalent is going to look like here. So on single thread GCC, we're able to get on just the x86 single core about 4,484 stocks per second out of just the GCC. And we start targeting the multi-thread. I get pretty much equivalent performance. It's a little bit slower, 4468 stocks per second on one thread. But we're going to start seeing more and more as I crank up the numbers of threads and target this. I'm going to go ahead and just clicking here. I'm going to go all the way up to 18, because I happen to know, since running this before, that 18 is the cutoff where Amdahl's law kicks in and the performance starts to go down. Even though we have up to 32 cores, 16 physical cores, but 32 virtual cores with hyperthreading. And then I'm going to run in the FPGA. And you can see here the performance is quite a bit higher than the MP-SOC or ARM version that I had. We were able to achieve pretty much better performance with multi-threading than we were able to do in the FPGA. So I got to about the equivalent to the ARM core with 2 threads on the x86. And just on using the CPU alone with 18 threads, I was able to get pretty substantial speed up of 35,000 stocks per second in just the CPU. And then by targeting the FPGA, unrolling the loop to about 16 times, the innermost loop about 16 times, which is about what you need to do to fill up the FPGA and use all the physical resources in it, I was able to achieve 52,000 stocks per second. So that's roughly, I don't know, we'll call it 5x faster by using the Xiilinx U250 FPGA. So there it is. I wanted to just respond to those comments and show you what this data would look like if you used x86 with the Xiilinx U250. So thanks for your time, and let us know if we can help you accelerate your algorithms. Thank you.